This video is an example of the kind of what I'm looking for in the post for this classwork assignment. You're asked to choose a claim and dissect it into a null and alternative hypothesis, as well as draw the distribution of the types of samples that you could get, as well as draw the sample distribution and shade in the regions that represent a left tail, a right tail, or a two-tail test. And also, you want to state or contextualize what a type 1 error and a type 2 error is for your particular claim. I pulled this example from the textbook. It's, I think, question 4 in practice problems of the chapter 9. But anyways, what you want to do is read the statement and try to figure out what the claim actually is. So if you read this statement, it says the mean entry-level salary for an employee at a company is $58,000. You believe it is higher for IT professionals in the company. So the implied in this question is that that's for everybody inside the company, it's 58,000. But if you're applying specifically for an IT position, then you expect the average to be higher. So you would claim the average salary for an IT professional is higher than 58,000. What we want to do is convert this claim into testable hypotheses. Those hypotheses for us are either going to be about population average or mean or population proportion. In this case, the problem is talking about the average salary, so we're going to state it as an average. Our goal is to state a null hypothesis so that we can use a sample average to help test its truth. But the way the claim is stated, it's easier for me to think about the alternative hypothesis first. An alternative hypothesis is always the opposite of the null hypothesis, but it is never equal to a number. I think the average is higher than 58,000. Higher than is not equal to, it's bigger than. So for the alternative hypothesis, we say the average is larger than 58,000. From there, we can figure out the null hypothesis. Remember, the null hypothesis always has an equal sign in it, and also the null hypothesis is always the opposite of the alternative hypothesis. In this case, we would say that the assumed average is 58,000. It turns out a hypothesis test requires us to assume what the average is, so that we can use something like the central limit theorem to test how far our sample is from the assumed average. For the most part, you should think of the null hypothesis as equaling a number, and usually it's the number given to you in the claim. So this is what part 1 of the post would look like if I were to post this. In part 2, you're asked to determine if this should be a left tail, right tail, or two-tailed hypothesis test. Keep in mind, you want to set up your test so you can get a sample to either support the claim, that is, be so extreme that it shows the alternative hypothesis is probably true, or a sample so that it's not so extreme that you default back to the null hypothesis. So we envision a possible samples along a number line with the center being the null hypothesis. We draw a normal distribution curve because that fits the central limit theorem. A sample average that would represent the alternative hypothesis would be much larger than 50,000. That would be the right tail of the distribution curve. That is, if we get a sample average that is inside that blue region, we should have evidence to support the alternative hypothesis and reject the null hypothesis. And if we don't, the evidence is not extreme enough to reject the null hypothesis, so we continue believing it's true. We call this kind of test a right-tailed test or hypothesis test for sample means because if we get a sample average that is so much larger, it's on the right tail of the null hypothesis, then we have reason to reject the null hypothesis. This is an example of what your second part of the post should look like. Run a null hypothesis test. It does test to see if the null hypothesis is true or not. The problem is the test can make mistakes. So that means there are 4 possible outcomes. You have the actual null hypothesis and it's actually true. But then you run the test, and the test tells you do not reject the null hypothesis. So the test is basically saying keep believing the null hypothesis is true. That would be a correct outcome. Or you run a hypothesis test and tells you to reject the null hypothesis. If your null hypothesis happens to be true, that would be a mistake, and we call that kind of mistake a type 1 error. Or you live in a world where the null hypothesis is false. You run the test, then the test tells you, don't reject the null hypothesis, keep believing it's true. That would also be an error, a type 2 error. Or you have a false null hypothesis, then you use the test to see if it's false. And in that case, maybe the test tells you to reject the null hypothesis. That would be a correct thing to do and no mistake. For 3, you're trying to just say, what does a type 1 error look like for your particular claim? For part 3, you just want to contextualize what it means to reject a good null hypothesis in your particular example. In this case, the type 1 error would mean or say that the test incorrectly says the mean salary for an IT entry level position is more than $58,000. So if I believe that, because the test told me that is true, I would go ahead and I would probably reject a bunch of offers that are around 58,000 because I think I should get more. A type 2 error tells you to keep a bad null hypothesis. In the context of my claim, that would be the test would incorrectly say that the mean salary for an IT entry-level position is less than or equal to 58,000. So if that was the world I lived in, and my test told me to interpret the wrong thing, I may accept the first offer close to 58,000 when really it's actually a low offer. So these two statements are what I'm looking for the 3 and 4.